Dichloromethane by Ethan McNeil, CH2Cl2. Dichloromethane can be found in oceanic environments such as swamps or other things, and it is also a clear liquid that looks like water. CH2Cl2's physical properties are that it's a liquid that has a boiling point of 103.3 degrees Fahrenheit and a melting point of negative 142.1 degrees Fahrenheit. Its uses are that it's used as a paint stripper or solvent that can be mixed with things, and is also used to remove caffeine from coffee. So for my Lewis structure of CH2Cl2, I had to have carbon in the middle because it started with carbon, and I had to have my two hydrogens on top and bottom because that's where I decided to put them, and my two chlorine is in group 17 of the periodic table, so it has 7 valence electrons, which means that it has to have 7 dots around it. So I connected all the bonds and I drew the different valence electrons, and that's my Lewis structure. The molecular shape of dichloromethane is a tetrahedral, and my ball and stick model had to represent that. I know it's a tetrahedral because I see that there are 4 bonds connecting all of the different atoms to the carbon. The bonds determine how many toothpicks that there are to connect to the different parts of my model. Speaking of my model, since I knew it was a tetrahedral, I knew that the hydrogen atoms had to be smaller than the other atoms, and they had to be at a sharper angle. The chlorine atoms on my model had to be larger than my hydrogen atoms, and had to be not as sharp an angle as my hydrogen atoms. And of course, the carbon atom is in the middle of the model and has all the bonds coming out of it, connecting all of the atoms. With the electronegativity of the carbon to the hydrogen bond, it is 2.5 to 2.1. The difference is less than 0.5, so that means that it's electronegative, and that the dipole is going to the left. With the electronegativity values for the carbon to the chlorine, it's 2.5 to 3, and it's equal to 0.5, so it's not electronegative, and it's facing to the right. The reason on my model that my hydrogen to carbon bond is shorter or smaller than my chlorine to carbon bond is because the electronegativity difference is smaller. Now with the polarity, because we know the electronegativity values, we can determine that the polarity is actually polar, although it doesn't dissolve in water, but it dissolves in other things because it's a solvent. And we know this to be true because when we add the dipoles, it goes diagonal on not completely to a 90-degree angle because it is a tetrahedral, but it is still diagonal nonetheless, which means it's polar.